Hello everyone, today I'm going to talk about our CPU design project. We did this homework together with my friends Faisal, Irfan and Mirai. Now we can move on to the presentation. Purpose of the project: we based the design of the processor named Fbu Cpu on the von Neumann architecture and used the state machine. It was tested with test codes in assembly language using control units and ALU systems. System architecture: the Fbu Cpu Rtl design is based on von Neumann architecture. It basically has four elements: custodians, memory, which is RAM, processing units, which is ALU, control units. The functions of the units used in the von Neumann architecture: memory holds operating instructions and variables, the processor unit performs arithmetic and logic operations, the control unit is required for decoding commands, storage are storage areas used in various tasks. Fbu CPU supported operations: the processor supports 9 instructions. Figure below shows the separation of the 10-bit instruction bits for the operation and the address of the Fbu CPU. Software used in CPU: the design was coded as a state machine. Case looks at the state and continues the progresses according to the structures within the state. The state diagram of Fbu CPU is shown in the left figure. The tasks that the processor needs to do step by step are shown together. The reason we use the status register is that the register, which specifies when all the mechanism in the system will works according to these steps. Condition cases. Case 0. In case 0, our register named program counter PC has pushed the value of the register where we keep the instruction in memory that we will execute, namely 0, onto MAR. Since we did not perform a write operation, we pulled our write signal RAM to 0 and increased the state by 1 and jumped to the state 1 after one cycle. In other words, here we gave the value of PC to MAR, thus we requested the content of address 0 from RAM, and when we change the state, RAM will return the content of address 0 from its own data output. Case 1. When we go to state 1, the instruction information coming from memory data out is written to the instruction register IR in order not to be forgotten. Since we will return to state 0 after the operation, we need to read address 1 instead of address 0, which we read before while the state is 0. For this, we increase PC by 1. After doing this operation, we increase our status by 1 to perform the new operation and move on to the status 2. Case 2. We check if the sixth bit of the register we assigned to IR in the previous steps is less than 6. The reason we check is that all operations less than 6 needs to read an address from RAM. We do not need to know the content only in STO. Since we need to read the content in the first 6 operations, the processor is designed with the logic of reading the content of all of them, then taking them to state 3 and finishing the remaining work in state 3. If the bits from 9 to 6 are less than 6, the address is kept in the first 6 bits of the IR, since we will need the address and the content of the address. We wrote this to the MIR of the RAM, so we want an address from the RAM again, but this time the address we want is the address written next to the instructions there. After these operations, we took the status tree. In other words, If it was one of the first 6 operations, we requested that information from RAM because we needed to read the address contents again. In other words, our status change depends on the first 6 bits. If the first 4 bits from left in our machine code were less than 6, we took the status to 3. If the incoming value is 6, we set the PC value equal to the number corresponding to the value of the IR from 5 to 0. We also return the status back to 0. In other words, the jump command actually arrived. We wrote the new value of PC. When we return the status back to 0, the PC value will be updated, so the operation we will read from RAM will now be the location of the code we will pull from RAM from the updated location, and we will have performed the jump operation. The feature of the seventh instruction is the conditional jump operation. If the account value is 0, we discard the PC value, the value of the first 6 bits of IR, and go to the state 0. If not, we do not change the PC value, we send the state to 0 without doing any operations. If command 8 arrives, no command, that is, no operation is performed. We just return the state directly to 0. If operation code 9 arrives, HLT is performed. That is, the code stops. We jump to state 4 for it to stop. Case 3. We use the first 6 operations to perform operation after reading from RAM. When we move to state 3, we directly move our future state to 0. In other words, after one cycle of the operation we perform, we go directly to the state 0. In the picture on the side, we set RAM and MAR equal to 0, but we can update their values in the operation below. If IR is equal to 0 from 9 to 6, it means that we are performing a LOT operation. LOT takes the content of that address and puts it into a count. We actually want to give the content of the state to MAR in state 2, and this comes to us from MDR out. After one cycle, we put it into ECK. When the operation code is 1, we assign the value inside ECK to the value inside the memory with the stow command. To do this operation, we gave the address of the place we set from IR 5 to 0 to MAR. We made RAM 1. At the same time, we load the data content of RAM. We also gave the ECK value to MDRIN. Here we gave the ECK content from the data port of memory. We made write in 1, and at the same time we gave the address coming from this STO operation. STO is a 10-bit number in its entirely, and we kept it in the IR register. When we gave 0 from 5 of the IR register, we gave that 6-bit address to MAR. When the operation code is 2, the add operation is performed. We performed the address content reading operation one cycle ago. The address we read came from the memory data read register out. We added it with ECK and wrote ECK again. When the operation code is 3, when the that is, the subtraction operation comes, when we have adapted the steps in the add operations to the subtraction operation. In other words, we subtract the value coming from the memory data read register out with ECK and wrote it back to ECK. When the operation code is 4, the multiplication operation is performed with the MUL instruction. The value from MDR out is multiplied by ECK and written back to ECK. When the operation code is 5, division is requested with the div command, but since it involves a complexity above our level, we will send the status to 0 without performing any actions when the operation code reaches 5. Case 4. In state 4, nothing is checked, nothing is done, it just loops over it. There is no exit command either, unless the processor's power is cut and then reapplied when the HLT operation arrives. It will not be possible to exit from state 4. Test cases. Testing software 1. For Fbu Cpu corresponds to the hexadecimal value of address 50 in memory, is loaded into the ACK register with the load command. The value of address 50 in our ACK register is added to the expression which corresponds to the hexadecimal value of A at the address 51. With the add command, the value of the ACK register, the sum of addresses 50 and 51, is F and is recorded at the address 52 with the sto command. The test is stopped with the hlt command. Testing software 2. For Fbu Cpu, the hexadecimal equivalent of address 50 in memory is loaded into the ACK register with the load command. The value of address 50 in our ACK register is multiplied by the expression A, which corresponds to the hexadecimal equivalent of address 51, with the MUL command. The value of the ACK register, I mean the product of addresses 50 and 51, is 32, 32 is recorded at the address 52 with the sto command. The test is stopped with the hlt command. Testing software 3. For Fbu Cpu, the operation we are asked to do is multiplication, but we need to do this with loops, not with the MUL instructions. The value at the address 51 in memory is recorded in ACK with the load command. 49 is subtracted from the value in ACK with the subcommand and recorded in the ACK register again. The result of the operation we performed in the previous step is checked with the JMZ command to see if it's equal to 0. If it's equal to 0, it exits the loop and goes to perform the operation at address 10. In other words, it loads the value of temp at the address 48 into the ACK register, records the value in ACK to address 52 with STO, and then ends the code with HLT. In this way, the result is recorded in memory without using the MUL command with loops. But if JMC is not equal to 0, account 49 continues to loop until it becomes 0. After the check, it loads the temp value to the address 48 with LOD. It adds the value to the address 50 to ACK with add. It goes to address 48 and records the value of the ACK to STO temp. It throws the value at address 49 into ACK and adds it with the value at address 46 and records it to the address 49 again. It returns to line 0, the beginning of the loop, with the jump instruction. As you guys can see, we outputted the signals for our codes with their hexadecimal equivalent values from Vivado with their hexadecimal values, as you can see. And the result of the project, the operations supported by the developed processor are taken from the Fbu Cpu ISA, which instruction set architecture table. When expressing the Fbu processor in the Verilog language, the ALU, arithmetic operation unit, is the section where arithmetic operations are performed. There are arithmetic operations in the Fbu Cpu. These are addition, subtraction, and multiplication operations are performed according to the incoming operation code and written to the ACK register. Test software which is test case 1, test case 2, test case 3 were tried one by one and examined on the simulation on Vivado. Our algorithmic thinking ability has improved and our command of the Verilog language has increased from this project.